These are processors that have thousands of cores. They're optimized for doing massive amounts of parallel work and being able to do that at once, but you're doing it in, say, half the time, and so you can do twice the amount of science. My name is Tom Papatheodore. I work at the Oak Ridge Leadership Computing Facility. I work in the User Assistance and Outreach group, and my focus in that group is on the people bringing in their actual applications that they're going to work on. So they're not leaving with just a knowledge of how to sort of use these new technologies with GPU computing on example codes, but they walk away with benefits to their own codes as well.
So what is it we do? So we were profiling working with 3 different versions of CCC. That stands for Convergent Close Coupling Theory. The 3 codes are basically, you can think of as atomic code, molecular code, and a code for heavy projectiles. So we've spent most of the time initially on the atomic code, and then we spent a lot of time molecular code, and ILCOM spent a bit of time on the heavy projectiles. Applications, so what we're solving is quantum collisions in atomic and molecular physics. These are small interactions between particles on atomic scale. The underlying theory is quantum mechanics, and applications have fusion energy, laser science, lighting industry, medical imaging and therapy, astrophysics. So initial profile of our code. Before we came, we did a lot of work with profiling, but we basically realized very early on where we will benefit from GPU implementation. And it was actually very, very clear what the new parallel structure should be. But while here, something rather unexpected happened. And that was that having had the allocation, a reserved allocation, decided to profile the full code in production mode. I think really if you're going to profile, you should almost always start from the production mode. Because all sorts of interesting memory things start happening when you are in production mode. And we discovered, to certainly my shock, is that there's a routine called get channel info, which gets information about channels, was taking about 39% of the time in a certain region, which was utterly crazy. And it's on the right, 100% memory access. Now I talked about that yesterday, and in fact this particular line wasn't being used, but I quickly fixed it up to, so what the issue, it was just an initialization issue. It transferred an array from A to B, and but it was done as a colon, so just a bit lazy in writing it. A equals B basically is what that statement said. However, because it was fairly large in the production mode, needlessly large, it generated a whole lot of memory access problems. So fixed that up, and so that was a surprise. Didn't expect that to be so much there. Then we're going to the profile of Dmitri's code, and that showed there that's 83% on one line. John expanded this out, so there's at the top 83% on just one line in the code. Fantastic, right? This is exactly what you want, because you know where to focus all your energies, right? So this is clear what we need to do. We've played a fair bit. We're trying to change this around. Needs some extra work. First of all, rewriting this particular aspect, and then once, hopefully I will demonstrate there is a new way to rewrite the parallelization, create or separate OpenMP away from GPU usage. This will run much, much faster in the longer term. Now, the other thing, so once it was clear for me that how to implement the new parallelization with the GPUs, I decided to address some of the long-standing issues that I've had about that I couldn't really understand. It seemed to me as if each node was behaving somewhat differently, and I couldn't figure this out. So our code is written with both MPI, parallelization, as well as OpenMP. And of course, one of the aspects that you want is that to have equal load balance across your nodes. And I create my own timing files, and I could see that on some cases that the balancing node, the balance between the nodes was relatively poor. You wanted well above 90%, but here were some cases with 80, 86%, and I couldn't understand why. So what was the goal in coming here? Well, of course, to learn a bit, have some fun. And this is an important point for me. So because I started 30 years ago, I've seen that at various points in time, I said, right, now we have to change. And of course, all of our students, ourselves, all of our careers depend, we live in the publish or perish world, and that's fine, we're used to it, it's just the way things are if you want to be an academic. So you can't afford downtime, and not just your own downtime, but the downtime for your students. So about 7 or 8 years ago, once it became clear that the dominant architecture was going to be loosely connected fat nodes, that the time was right to implement MPI. Well, now is the time for that third generation. Now that there's 16 gigabytes and we promised even more on each GPU, this is very, very real, very, very practical, and this is going to be an exciting year because 2018 is when this is going to happen. So this particular graph shows the outcome when I changed that initialization from the lazy A equals B to just utilize that part of the array that was required. So it went from almost 40% in that you saw earlier to sub 5 to around 5% here. And John made this lovely graphic. What previously was taking time up here is now shrunk into this part here. So that was a delightful outcome of this. This is what we did yesterday afternoon. And after we did that, whilst I was attempting to sleep last night, at 3 o'clock in the morning, I realized, I wonder if that's been our problem all along with load balancing as well. So I got up and I resubmitted my jobs to see, well, how has this affected load balancing? It's fixed it. So very, very happy. You can see on the right these numbers now compared to what we had before. So without even any GPU usage, actually fixing that particular initialization, which then in turn also helped to fix load balance, has resulted in almost a factor of 2 speed improvement without any GPU usage, and only made possible, as John Stone pointed out yesterday, due to the new profiler, because the profiler was able to point to the line. So with old profilers like even gprof and tcov that we would have used, there was no way we would have found that this line of initialization is where the time goes. But that profiler did that for us. Okay, so poor performance became visible at production scale. So that's a really important lesson, certainly for me, is that if you're going to seriously profile your code, start and invest time in running a production run. Start there. Also, very grateful for those 8 nodes reservation. Couldn't have done these production runs really fast without that. Absolute critical. Thank you so much for the help in that regard. Next steps, wish list. So this is what we will do. I'll have to rewrite the OpenMP parallelization. It's clear what needs to be done. It's quite intensive. Would like to be clear that we will continue to have access to GPU-based nodes, because if we want to invest our time in developing this, it would be really nice to be beneficiaries of it. Was it worth it? Absolutely. We achieved much more than expected. Certainly it's been the most valuable week for me for this year, and our emotional scale, it started fantastic and it got better and better and better as we progressed. Great. Thank you very much.